Okay, we're moving on to a little smaller scale in the weather. Something you all deal with, and it is extremely important for aviation, is thunderstorms. So we'll start with them, and then we're going to move on to local wind system, which also can be pretty complicating factor for your flying. So think about the weather. We've talked about parcels of the air moving upwards, and a thunderstorm is just that. Convection is a parcel of air that is unstable. In other words, it is warmer than the surrounding air, so it wants to accelerate upwards. Here we have an example of that. Oh yeah, if the air is going up in one area, it's coming down in another. That other area may be fairly broad, maybe very tight, but not all the air can go up. Some of it must come down. So you'll notice here in this image, we have air going up in the thunderstorm, cooling as it's going up, and around it, there's sinking air. So what might cause the first lift that might do it? It would be a frontal system, probably. We know fronts, cold air is denser than warm air, so it's going to tend to push the warm air aloft. As it does that, it's going to tend to make that air rise. That air parcel is going to lift. We wind up with a thunderstorm. As that parcel lifts, if the atmosphere is unstable, and that is a key word here, if it's unstable. Here they have a little temperature sounding. You notice it's fairly stable right in this area, because here's the cold front down below it, which is lifted up. There's a little warm layer here. The warm air comes in, and then it gets colder again. Well, if you can push the clouds through that air parcel through this layer, then it would tend to want to rise. So the key with this one is the front lifting the air enough, lifting those air parcels enough to get through this layer so it can keep on rising. In this case, we're depicting it as yes, it is. So I want to talk about radar. Radar out there now, what we have is dual pole radar. So this is an image of dual pole radar. I wanted to find someplace that had some echoes today. High resolution and at the lowest elevation. So what do I mean by lowest elevation? Well, if you're looking at a radar, if you were able to look inside the dome, you're going to see a dish. That dish rotates around and it elevates upward at the same time. So in other words, it may take a scan all the way around and it's at half a degree. It goes around again and again. Each one of those scans is looking, and it spends most of its time listening. It sends out a pulse of echoes and it listens for a little bit. So, and then it will gradually rise to another elevation and do the same thing till it eventually reaches the top of its elevation angle, which is 19.5 degrees. So when you look at radar and you see it from the National Weather Service, know two things. Either you're getting one elevation angle, which probably is the lowest elevation. So that would be if you were flying at a lower level. But you also could get what they call composite radar, which you're getting the maximum return at all levels composited into one image. So in other words, the highest radar reflectivity might actually be at maybe not a half a degree, but maybe 1.5 or 2.5 degrees. In thunderstorms, many times you'll see that. The stronger echoes are further up in the cloud. One of the nice things about dual pole is you can Doppler radar is you can also get a velocity data. Here is base velocity data. And hopefully it will come in for me here. But if it doesn't, what you can find is that parcels are moving. It's just a Doppler effect. Say a train goes by you or a car goes past you, and you can hear a change in frequency. That change is what we're reflecting here in the parcels, the returns. And notice here, this is 0. So in other words, if you were to draw an arrow from here to here at this elevation, this is the wind direction. Closer to Boston, closer to the radar, lower levels, the winds is out of the south. Up here, more northwest. So it's interesting to see how the wind direction changes with height. And that is something you actually see with the velocity data, because remember, things going out a half a degree. That half a degree starts out at one elevation, and maybe 100 miles out, that elevation is significantly higher. So it's looking up into the higher part of the cloud. So that is why I can depict that I'm seeing different elevations with this radar. Finally, the differential dual pole. Dual pole looks at the shape of the radar echo. It gives you a two-dimensional picture of radar echo. So in other words, if I have a ice crystal out there, maybe that ice crystal is all fragmented and kind of weird shaped. Dual pole is going to depict that as kind of a weird shape. Maybe you'll have a rain droplet or a snowflake. Each one of those is going to look different and be depicted differently by dual pole. By that, I can tell where the melting level is, what type of precipitation is out there. So if I were to look at Boston's precipitation right now, if we get it back here, yeah, we can see we have actually rain out over the water and snow to the north. So if I was looking for a melting level somewhere closer to the ground, probably right around Boston, a little bit south of Boston, the precipitation is changing over to rain, while north of Boston it's mostly snow. That to me, if I'm making a forecast, and you as a pilot, if you were flying in and out of Boston today, you would want to know that. Oh yeah, I'm coming in from the south. I may be having rain coming into the airport, but I may transition to snow as I get close to the airport. All these are aspects of things you're going to want to know as a radar. So taking that into account, now let's move on. Oh yeah, there's different various types of thunderstorms. Most thunderstorms in the summertime are individual storm cells. In other words, if you're able to look at them, you can probably fly around them. They're not going to get more than about 30 to 40,000 feet high. Now, this time of year, we can get extreme thunderstorms called supercells. What they are, they must be rotating, and they're going to have a tremendous updraft coming in, and right next to it is going to be a tremendous downdraft. If you were to fly a plane through that thunderstorm, you would probably run into 100-mile-an-hour winds up and 100-mile-an-hour winds down. I don't think you want to do that. By the same token, if you're flying between thunderstorms in the wintertime, we'll say, or in the spring when there are intense thunderstorms around, well, that thunderstorm with all that flow down might actually be creating an echo an area where there's no echo, or very close to it. So it's something to be informed about in the thunderstorm. Watch out for areas near it where maybe beginning new thunderstorms may be just popping up. May not even have gone yet, but the airflow may be very tremendous. So give supercell thunderstorms a very wide berth. I wanted to do just a quick look. The other day we had lots of severe weather. And here is looking just at the upper air. And we'll look at 850 millibars. The green is moisture. There is a tremendous amount of moisture feed coming in. Remember, moist adiabatic lapse rates are significantly less than dry adiabatic lapse rates. So the more moisture you have in the air is going to condense, and that means it's going to put out heat, and you're not going to wind up with a lapse rate, which basically is temperature cooling with height, nearly as great as you are in a dry atmosphere. So we have a lot of moisture. Look at this, 30 and 40 knot winds here. If I were to look up at 500 millibar at the same time, I would see very much more of a southwest flow. And the divergence, well, we're always interested in divergence aloft because it allows the air to lift. I have tremendous jet streak here coming out, and you'll notice over Oklahoma, Arkansas, in this area, there is a lot of lift that's going on. And say I wanted to look at the upper air soundings for this time. And the reason I want to look at them is let's take a look down here in Arkansas. We looked at all that moisture coming into that area. This is a skew T, and it's one I like. The reason I like it is, yes, you'll notice here you can look at the moist adiabatic lapse rate, and that is what this is. So if I have an air parcel down here that's lifted up, this is the temperature of that air parcel. Now, reality, here's the temperature of the outside air to that. Notice the difference, the spacing. A skew T allows me to look at this area and say, oh, the bigger this area is, the more unstable the air, the more power that air parcel has. So if I can lift this air parcel right here upwards, I know that all the way up to 9 kilometers or more, I am warmer than the surrounding atmosphere, and then I finally turn colder. So I am kicking an air parcel all the way up here. Oh yeah, interestingly, if I have tremendous, this is an acceleration up. Unstable air accelerates, so the more I accelerate upwards, the further up above the point where it would have normally stopped, that cloud top's going to go. It's called an overshooting cloud top. If you're flying high up and you see a cloud that looks like it's well above the surrounding cumulus clouds, that has the most strongest updraft in it. You're going to want to avoid that area. So this is just an example of what you can see here. One other thing that's very interesting with this is I wanted to show wind shear. Wind shear, just a change in direction. Notice low level, southerly flow, turns westerly, and we wind up literally within a few thousand feet of the surface, 50 knot westerly wind, and then it gradually turns even to the southwest and even stronger. You have a lot of wind shear here. The wind has changed with height, both direction and speed. So all that is enhancing all of this today. We're going to move from thunderstorms now into local winds. Local winds are like sea breezes. They can be mountain breezes. And today we have a great mountain wave going on off the Appalachians. There's an intense low up here, pushing very strong west winds across the Appalachians. You get this in the Rocky Mountains, but in the Appalachians today, you can see the wave pattern. If you're flying west and you're going to be hitting the initial wave out in here, it's not going to be too bad. But as you approach, you're going to bounce more and more until you get to the west side of the mountains and get away from that wave. You can also see the moisture coming off the Great Lakes down into here, causing convection. So this image has a lot of what we just talked about with local circulations. Around here with sea breezes, I get them all the time. I had one this week when I went down to the ocean front. All of that is part of what you're going to do with. When we talk about stable air helping mountain waves, this is a sounding today from Blacksburg, Virginia, which is right along the eastern mountains. Notice 65 knots, 55 knots, 30, and 25. Pretty strong northwest winds. Northwest winds are downslope, so they're hitting that, and the air there is very, very stable. Think about it. If I am coming down a mountain, I'm pushing an air parcel down. That air parcel is very stable, but I am still pushing it. It's going to want to bounce back to where it was, but it doesn't have the ability to do that with like it would with unstable air. So when it tries to bounce back, it's going to come up and bounce to a certain point and then stop. That's why during these mountain wave events, when the air is fairly stable, you can really wind up having very, very nasty mountain waves by the mountains. And that is what's going on today here. If you were flying into the Appalachians in a small aircraft, I know the jets, commercial aircraft, can fly over this with no trouble. But they do got to realize it's going to bounce when they're hitting an airport. And turbulence is part of all of this because the wind mixes and all your local circulations. So this is just something what we're talking about this week. Hope you got a little bit out of that. Let me know if you have any questions.